So right here I have an initial value problem. dy dx equals tan squared x plus y, and I have the initial condition that y of pi is equal to e. So the fun part now is using the reduction to separation of variables to solve this. So first of all, we clearly see a linear function in this tangent, this x plus y. So we're going to go ahead and say that w is x plus y. Hopefully that registers as a w. I know it looks a little bit choppy, but dw is then dx plus dy, and hopefully you see the direction everything is going in. I honestly thought of this on the fly, but I was hoping to find something that would involve more than just the substitution. Bring back a little bit of pre-calculus. So if dw is dx plus dy, then trying to find a substitution for dy dx, that would bring us to dw dx equals 1 plus dy dx. And so that means that dy dx is equal to dy dx is dw dx minus 1. So now bringing this expression and subbing it into this here equation, upon doing that, taking dy dx equals tan squared x plus y. Since dy dx is dw dx minus 1, and tan squared x plus y, that's just tan squared w, we end up with dw dx minus 1 equals tan squared w. So dw dx is tan squared w plus 1. And from the trig identities, tan squared w plus 1 is secant squared w. So dw dx is secant squared w. And if you need to validate that, you can always take sine squared theta plus cosine squared theta equals 1 and divide the cosine squared theta. You will end up with tan squared theta plus 1, which is equal to secant squared theta. So now we have dw dx is secant squared w. So I'm going to multiply out the dx and divide the secant function, and I will end up with cosine squared w dw equals dx. Or I could just go ahead and say cosine squared w dw, scroll down here, minus dx equals 0. And at this point I can then integrate everything. So integrating everything on both sides now, the integral of this cosine squared w, that's going to be the more challenging one. Hopefully you remember the double angle identities. Cosine squared w dw minus integral of dx, that's equal to the integral of 0. And the integral of dx is just x. The integral of 0 is the constant of integration. This cosine squared w, on the other hand, we need to break it down using the double angle identities. Recall from trigonometry that cosine squared theta is equal to 1 plus cosine 2 theta over 2. Or, and since we're using w instead of theta, I'm going to go ahead and say 1/2 plus 1/2 cosine 2w dw minus x equals c. So I realized that I wrote above was really choppy. It wasn't neat. neatly written by any means. So 1 half plus 1 half cosine 2w dw minus x equals our constant of integration. So I could easily factor out the 1 half out of that integral, but realistically it's not going to make much of a difference in terms of difficulty. So in evaluating the integral, I would end up with w over 2 plus 1/4 sine 2w. Remember, you have to use substitute when you integrate the cosine 2w, and you will divide out the derivative. So that's how you end up with 1/4 instead of 1 half. Nevertheless, upon integrating the 1 half plus 1 half cosine 2w dw, I end up with w over 2 plus 1/4 sine 2w, and I'm subtracting from that x, and it's equal to the constant of integration. And so earlier we said that w was x plus y. So upon substituting that in, I end up with 1 half x plus y plus 1/4 sine 2 x plus y minus x, and that is equal to c. And the initial condition that was defined in this problem now, it was that y of pi was equal to e? Hold up, let me actually validate that. Okay, so I validated that, and the initial condition was that y of pi is equal to e. So now we have this function f of xy, and it's equal to our constant of integration. And earlier I said it wouldn't make much of a difference if you set everything equal to 0, integrated 0, and then ended up with the constant. And it might have. I actually like doing that for initial value problems, as now I have my constant consolidated, so I could just plug in x and y accordingly. And so we know that when x is pi and y is e, that is equal to the constant of integration. So if I plug in those two values, I end up with 1 half pi plus e plus 1/4 sine 2 times pi plus e minus pi equals c. So that is the value of our constant of integration. So the particular solution to an ordinary differential equation is always something, well, in this case it's going to be in the form f of xy equals c, and since we have the constant of integration solved for, that comes out to, let me actually write that in green, and this is going to be a little bit sticky to write, but do bear with me. 1 half x plus y plus 1/4 sine 2 times x plus y minus x, and that equals 1 half pi plus e plus 1/4 sine 2 times pi plus e minus pi. And this is the final solution to this equation here.